Hello everyone. Today I will present our work entitled Evaluating Physics Informed Feature Engineering for Surrogate Modeling of 4D Printed PLA Beam Morphing. The main question of this work is simple. Can we improve small data surrogate models by adding physically meaningful features derived from the original printing parameters? Before presenting the motivation, I would like to briefly clarify two terms used in this presentation. First, 4D printing refers to 3D printed structures that are designed to change shape over time when exposed to an external stimulus. In this work, the external stimulus is thermal activation, and the response is the morphing of PLA beams. Second, the terms FFF or fused filament fabrication and FDM or fused deposition modeling are used here to describe the same extrusion-based polymer additive manufacturing process. Both refer to the layer-by-layer deposition of thermoplastic filament. The motivation for this study is that thermally activated shape morphing in FDM printed PLA structures is promising for deployable and shape-changing components. However, the final morphing response is not controlled only by the nominal slicer settings. Parameters such as printing speed, layer height, nozzle temperature, and bend temperature are important, but they do not fully describe the internal thermomechanical state generated during printing. During FDM, several hidden variables are introduced. These include residual stresses, layer-dependent cooling histories, imperfect interlayer bonding, and local variations in polymer orientation. These factors are difficult to measure directly, but they strongly influence the final morphing response. The objective of this study is therefore twofold. First, we introduce a physically grounded proxy for the morphing response based on the bilayer effective coefficient of thermal expansion framework. Second, we evaluate whether machine learning can predict this physical proxy directly from the nominal FDM process parameters. The experimental dataset consists of FFF printed PLA beams. For each printing configuration, 3 replicate specimens were produced and measured. 6 process parameters were varied, that is, activation temperature, printing speed, layer height, extrusion width, nozzle temperature, and bed temperature. In total, we used 80 unique configurations, which have good coverage of the 6-dimensional processing window, while keeping the experimental campaign feasible. For modeling, the 3 replicate measurements were averaged, so each response variable, R1, R2, and R3, was represented by 80 mean values. This slide summarizes the full workflow. The upper row shows the experimental route. First, we print a flat PLA beam using the selected FFF parameters. Then the beam is thermally activated. After activation, the beam morphs into a curved shape. From this final shape, we extract the 3 geometric responses: R1, the chord length, R2, the deflection or arc height, and R3, the internal arc length. The lower row shows the modeling route. We first construct the input feature set, either with 6 raw features or with 6 plus the 3 engineered features. Then we train 3 surrogate models: MLR, RSM, and kriging. Finally, we evaluate the models Using fivefold, group k-fold cross-validation, grouped by configuration, and compare accuracy for each target response. This is the central result of the presentation. The plot shows root mean square error values for R1, R2, and R3. Lower root mean square error means better prediction. For MLR and RSM, adding the engineered features generally gives a small improvement, especially for R1 and R3. The improvement is not dramatic, but is consistent enough to suggest that the physics-informed features are adding useful information. For R2, the difference is much smaller, which means that arc height remains difficult to predict. Kriging behaves differently. When the engineered features are added, kriging does not improve and in some cases becomes worse. This suggests that the larger 9-dimensional input space is problematic for a distance-based method when the dataset has only 80 configurations. The main interpretation is that physics-informed feature engineering improves the surrogate models, but the improvement is modest and depends on the response variable. The clearest learning signal appears for R1 and R3, which describe the overall scale of the morphed beam. For their responses, the approximate cross-validated R-square values are in the weak to moderate range, about 0.3 for R1 and about 0.5 for R3. In contrast, R2, which represents arc height and is more directly related to curvature, remains close to zero. This suggests that R2 is not well captured by the available nominal printing parameters alone. A possible explanation is that curvature depends more strongly on local mechanisms, such as residual stresses, cooling history, and layer level variations, which are not explicitly measured in the current dataset. To conclude, the results show that physics-informed feature engineering can improve surrogate modeling, but the effect is model dependent. The engineered features modestly and consistently improve the parametric models, especially MLR and RSM. This suggests that simple physical transformations of the input parameters can help these models capture part of the morphing behavior. However, the same features do not improve kriging and can even reduce its performance. This highlights an important limitation in small datasets. Adding more dimensions is not always beneficial, especially for distance-based or interpolation-based models. Overall, RSM with engineered features appears to offer the best balance between predictive robustness and interpretability. For future work, we plan to test more advanced machine learning models, such as random forests and gradient boosting, and to investigate data augmentation strategies. Thank you very much for your attention.